how to assess your test code quality. So usually we speak how to assess our production code quality, but now I'm going to speak how to look into your tests and understand if they're actually testing what we're expecting them to test. So my name is Vaidas Pilkauskas. In the meanwhile, you can follow me on Twitter. This is my Twitter handle. And with no further ado, let's a little bit look what I do. I'm a Vilnius Java User Group co-founder. I'm also facilitator of Code Retreat events. If you don't know what it is, please go to coderetreat.org. Actually, tomorrow is Global Day of Code Retreats, and I think all over the world, in most of the cities are hosting their own code retreats, so check them out. And I know there is one in Vilnius. Also, I'm going to be in Kaunas and going to facilitate one there. This is a free event organized by community. Just if you haven't been there, just please go. It changed my attitude towards software engineering a lot. During my day, I work at Wix. Wix is a website builder platform. At Wix, we are most of engineering is developers, and I take a fancy name. My title is Server Guild Master, which means that I do a lot of coding, and also I help our people. I mentor those people, and deeply care about design and test-driven development. During my spare time, I'm a bicycle rider. If you happen to be in Vilnius and you don't know any good trails, just ping me. I will definitely help you to find something interesting here. It's the perfect town to live for a mountain bicycle rider. Okay, and this presentation was prepared together with my good friend Tadas. He's now living in different city, different side of the Europe, so he couldn't co-present with me. So thanks to him. And before we go into serious stuff, I would like to ask how many of you like music? Okay, a few. And how many of you know what Bantu Rider is? Okay, at least one. So perfect audience, I will tell you what Bantu Rider is. Bantu Rider is a contract between the band or band's manager and concert organizer. For example, if you're going to if you're a piano player and you are going to perform in some place, you usually have some requirements for that place. For example, maybe they need to bring some brands piano to be played because you're not. It's like really expensive for you to carry this piano all the time in your tour. So those requirements can include hospitality requirements. For example, if you're vegetarian, maybe you want to eat vegetarian food, or maybe you need some number of towels, and so on and on and on. And some are technical. For example, like some equipment needs to be present at the stage, and that's so that you can perform. And for performance to be good, you actually have to fulfill all those requirements. So you sign similar contract, and the contract is named Rider. And I'm going to speak about Van Halen's 1982 Bantu Rider. And at that time, Van Halen was a super big star band, and their performance was really big thing, and they were putting a lot of equipment on their stage. And at one show, organizer didn't read their requirements carefully, and stage collapsed, which nearly caused one member to be killed. So they decided that, okay, we need to do something. We need to add something into our contract so that we can understand if people actually are reading that contract. And what they did, this looks really pretentious and crazy. Like what they asked, okay, please present M&Ms in our dressing rooms, but please absolutely no brown ones. And then each time they went to the dressing rooms, they can check and verify if everyone has read the contract. If they find a brown one, they can say, okay, we're not going to perform, we're just taking a fee for the concert and going home, because in that case, they cannot predict what happens on the stage. Probably people will die during the concert or something. So this is what they did. They added a small thing to their contract to verify if the thing was read and people are actually going to comply to it. So looks smart. Okay, so today's agenda is test quality and code coverage. Then mutation testing in theory. I just want to ask you, who knows what mutation testing is? Okay, a few. Cool. Great audience. Because this is an introductory talk, I'm going to explain what it is and what is not, and how to use it and how to benefit from it. And as I say, like I'm going to speak about mutation testing in theory, and then in practice. In practice, I'm going to talk about Java tool, which is probably the most mature on the market at this time. But you don't have to be a Java coder, or you don't have to be a coder at all. This is mainly an example of what you can achieve with the tool, similar like this. Okay, so before we go, let's talk what production and testing code quality is. When I say production code, it's everything that runs in production, including your deployment scripts. When I say test code, everything that tests that your production and deployment scripts work correctly. So simple as that. And we can say that code has bugs, and we can say also that tests are code. So it happens that tests also may contain bugs. And who actually watches the Watchman? Who actually can verify this? And of course, the answer is Chuck Norris. But Chuck Norris is a single person in the world. Even if he is capable of doing amazing things, we cannot trust that he is going to be near us and help us like when we need him. So test quality. We're used to define test quality as like by looking at our source code. They should be readable, they should be focused, concise, and well named. But there is something missing here. Like if we even make our test like this, can we say that they're actually doing what is expected from them? And today we're going to look at that. So even though that you are do a lot of testing of your production code, you're never sure that you actually caught all of the bugs that exist in the code. And let's go into code coverage. So who are using code coverage or has code coverage goals in their teams? Okay, no one. Oh, okay, a few. So if you do that, it's a great tool to understand it and learn a lot about your system and how much tests are actually executing of your code. So let's look up into this tool. So types of code coverage. So one thing you can, definitely most of the programming languages have is line coverage. So if you have a source file and if all of the lines are covered, like at least you execute something with that line, so you can say that you have 100% line coverage. Also, there is a branch coverage, which goes even deeper. For example, if you have Boolean logic in your lines and some conditionals, like ifs, whiles, and so on, to cover fully that line, you have to execute all the conditions of that line. Otherwise, it just like touches only part of it. There are also instructions. Instructions, since, for example, in Java, you write maybe simple command, but under the hood, it translates into multiple bytecode instructions. And depending how you write that Java statement, it may translate into different bytecode instructions. So to cover that, you need to like do different things. But usually people don't use instruction coverage. Also, there is a cyclomatic complexity, which says that for example, if you have a loop that loops something 10 times, to have a full cyclomatic complexity, you have to execute that loop 10 times. And if you have infinite loop, is it possible to achieve cyclomatic complexity coverage? Probably no. Also methods and many more. So this is an example of JCoco. JCoco is a tool for Java developers. This is an example of their report. So what it says that what is really important that I see what is completely not covered with my tests. So I can go and clearly answer that, okay, this part I'm not testing at all. I'm not looking with my test into this part. This part, I know that some tests will cover it, and this diamond says that, okay, I have covered part of it, so this is branch coverage result. I covered part of it and probably forgot to cover another part. So quite useful metric, like you can look at it and understand how deep your tests are executing your code. Okay, so line coverage. Given that we have something simple like this for our example, to get full coverage with line, what we need to do, we just need to write a simple test which asserts that, okay, we just call this one and expect this one. So we got 100% of line coverage. Now, when we have a branch, to get 100% of line coverage, it's still like enough to have one assert. But if we want to have full branch coverage, we have to write 2 tests. So this is a difference. And if you have really complex lines which involve a lot of Boolean logic or branch decisions, you will have to write additional tests, even though that your tools may show that you have 100% of coverage. So it's easy to fool yourself by just looking at the report. This is how we show our managers that we have 100% of the tested system. Okay, so can you trust 100% of coverage? So code coverage can only show what is not tested. Remember that red part. So you're definitely sure that we haven't done anything about it. So this is where code coverage helps. And if you're using interpreted language like JavaScript or Ruby, if you have 100% of code coverage, you get additional benefit that you're executing your code and at least you know that your code has correct syntax. So it's like compilation for statically typed languages. And code coverage can be gamed on purpose. For example, someone sets you a goal to get maybe 70% of code coverage, and you just execute your system in your tests, but don't verify results of that system. And you can fool and code coverage will be completely green, but you will not be sure that you are testing correct results. And it can be, and it can happen by accident. Like if I'm not writing test-driven development or something that ensures that I only write as minimal part of the code that is needed by our tests, I can forget also assertions. I can quickly be interrupted by my colleague, and I see, okay, test is green. Let's go to another one, and it's completely not what we wanted. Okay, so there's another, like, code coverage is useful. I'm not going to say that you shouldn't use it, but there are tools that actually are looking into test quality and test coverage. So code coverage is something that your tests are covering, and there is another thing which is called test coverage. So test coverage is about mutation testing. And mutation testing is, the principle is that you introduced some small change. Like remember that example from Van Halen's tour. You introduce some small change and you expect your test to fail at that time. So this is the point, like you're not breaking, like you're not writing additional tests to break your system, but you're changing your program and you expect your test to fail. So a couple of examples. They are not, this is not exhaustive list, like there are many things and it depends on the tool, it depends on how, like it's just a theory, like, and this is only a few examples what it is. So you have such a program and this is what you can do with it. Like you can change operator from equals to not equals. You can just always return a constant. You can return null. And if your test doesn't fail after this, you have a problem with the tests. So this way you can prove that your tests probably don't test everything that's needed. And another thing what code coverage is not, if you're refactoring your program and you're just getting equivalent functionality, it's not mutation testing. So this is mutation testing, and if you're just like improving your program structure, it's not mutation. It would be equivalent to the previous program. Maybe it would be more readable, but from the tool's point of view, it's equivalent. Okay, terminology. Applying mutation to some code creates a mutant. So you just change some small bit in your program, and you have a mutant. Then, if your tests are passing, if they are still passing, it means that that mutant survived. So if we like mutants, let them survive, but this is actually opposite of good thing. And if tests fail, it means that mutant was killed. So if we introduce mutant, we expect some test to fail. This means that that test has caught the mutant. So failing is the new passing. Like if in regular testing we expect everything to be green, in mutation testing we expect that tests don't pass. With this, I want to give you an example of algorithm, how it can be developed using test-driven development, and how mutation testing can prove that we are maybe doing something wrong with it. So what I'm going to do, I'm going to take an array, like of arbitrary number of elements in it, and I want to find the largest number in that array. So basically, I need to implement function which finds a maximum of that array. So first of all, what I'm going to do is I'm going to write a failing test. So I don't have any production code yet, anything. I'm just to have a failing test. And this is my first step. So I'm going to say that given one element array of 0, I expect that the largest number is 0 in that array. And for this to pass, what I do, I simply implement it this way. I return 0. Simple as that. I don't have any more requirements in my tests. Next thing is I'm adding another test. This time I'm checking with different input. So I have to fix this part. So what do? I say, okay, let's return first element. Again, passing. Now, I understand that, okay, I cannot just play with this really long. I need to check multiple element array. And in this case, it's like the largest one is 2, and it's 2. So what do? I just come up with some kind of implementation. And it looks like it. Like if you have done, it's a simple example, and we know that probably this is correct. And I also check my code coverage, and it's green. Everything is green, except this part, which is, because I don't create an instance of the class, it says that, okay, you haven't ever used constructor of the class. I only use static method. So I have 100% of code coverage, and it looks fine, right? Let's see what mutation testing can do with this example for us. So we have the same implementation, and we will introduce mutation testing here. So we will say, okay, let's see what happens if we add true. You know what happens? Our tests still pass. And it comes out that we only need this implementation for our tests to work. So it means that we actually wrote more code than was needed by our tests. And to continue, we add another test which proves that, okay, we actually need more code to implement fully an algorithm. And we come back to that implementation. So what just happened is that baby steps matter. And test-driven development is all about writing minimal code and refactoring. And because we're human, we accidentally introduced a mistake in that code. We have written too much code because we're so much biased, and it's so easy to write a lot of code without even thinking like if that code is doing correct thing or is it doing too much. It was a little bit over-engineered. And mutation testing showed us, like, you're writing to not so, like, you don't exhaustively testing your solution. And what we had to do, we had to come back and go with baby steps. And with this, we can say that tests' effectiveness can be measured how much mutants we catch. If we introduce a mutant, and if we catch it, we can say that our tests are effective. It's like hiring a hacker and asking him, can you please break into our system? Like, can you do something bad and just tell me how did you do, because we want to improve. So what if mutant survives? So as you saw, I simply deleted the code, find the simplest implementation, and then rerun everything. Or you can add additional tests. It actually depends very much on how you work. Those are kind of equivalent, because in the end you're either adding tests or you're deleting code and then adding tests. So it's matter of the way you work. And in test-driven development, minimal amount of code is to pass the test. So this is the essence of how you can benefit it from test-driven development. And the challenges. Okay, so first challenge is that it's quite high computational cost. For example, if you're introducing mutant into your class, you have to run whole test suite one time. If you're adding another, you're repeating that. If you have a lot of code and you're like mutating it a lot, for each mutation you will have to run it. So if your tests are very slow, it will be order of magnitude slower after you introduce this one. Also, equivalent mutants. For example, if a tool that you're using changes your program into completely equivalent implementation, it happens. Like I will show you an example. And also infinite loops. For example, if you have while statement and you change its Boolean expression into true, it becomes an infinite loop. So this is equivalent mutations. You can see that we have a while which checks like while not equals 10, but we can also translate it to something like this. Usually a good practice is to write code like this, because this one, like tools, good tools only mutate this one to this one, not backwards, because this one is a bit stronger. It checks, it has, it checks if like it's not inclusive. It's easier to make a mistake here. And infinite runtime, so you just have an expression and you change it to infinite loop. And how to deal with infinite runtime, all the tools, they have timeouts. So if you get into infinite runtime and test starts to run forever, after some time it terminates. Okay, so is it really slow? So I told you, like if we have, for example, a huge code base, like in our example, we're taking like 300 classes, and let's say that each of the class has, in average, like 10 tests, and one test runs around 1 millisecond. So total test suite runtime is about 3 seconds. Quite acceptable for such a huge code base. Now what happens if we introduce 10 mutations per class? So we get 3,000 mutations, and if we run each time, like with all of those mutations, we run our test suite, it happens to be 150 minutes runtime. Completely unacceptable. Can we do anything about it? Yes, we actually can do, and great tools use heuristics to detect what is important in your tests. So for example, if you have 300 classes and so on, like in previous example, you should run only tests that are covered by that mutation. So you are using your code coverage tool, and you see, if I run this test, which part of the code is covered by that test? And then, if I mutate that code, I can say, okay, I only need to run those tests that cover that code. So this way we can save a lot of runtime time. And in our case, total runtime can shrink into 30 seconds, which is quite acceptable. For example, if you run it on your CI server or before building and releasing to production, this is quite acceptable. It's not 150 minutes, only 30 seconds. And even though, like, if you're developing and using test-driven development, you expect a really quick feedback. So for that, you can do another thing. You only run mutations on on those things that you actually have changed during the development. For example, you're changing one file, another file, you only run tests on those files. And then you know that, okay, if there are like any changes in mutation, because previous things can be, they're not changing and you always are getting the same results. So usage scenarios. So continuous integration. So just add to your automation system and expect it to build and maybe send a report. Use TDD with mutation testing only on new changes. So if you're doing test-driven development, expect a quick feedback from mutation tool. And also try adding to your legacy code. I think this is the most useful, at least from my experience, because if you are doing TDD, you usually learn very quickly to write a quite quality code. But if you look into something which is huge, you can detect a lot of interesting patterns, and maybe you'll learn a lot about your tool, about your code base. So just add it to your legacy project, but don't fail a build, because if you will fail a build, people will get angry and they will not do anything, because it looks in legacy project you cannot fix everything like in a couple of minutes usually. So produce a warning report and discuss those issues, but be very careful. If you, for example, have code which does some nasty side effect, for example, deletes files from file system, and you're passing it like particular path where maybe some cache has to be deleted, and if your mutation testing tool is so smart enough that it will replace with the root folder and you're running as a root, it will delete all the files from your system. So be careful of what you're doing. Sorry. Okay, let's talk about tools. So Ruby has Mutant, it's quite mature tool. Java has Pit, probably the best on the market. Python has Cosmic Ray, JavaScript also has, and so on and on and on, and there are many tools that are unmaintained. So let's talk about Pit. Pit is an active project. It has really great reporting. Unfortunately, no Scala support. If you're working with Scala, it's very hard to write mutation testing support in Scala. And Pit originally stood for Parallel Isolated Test, but now it just stands for Pit. It has nothing to do, I think, anymore with parallel isolated tests. So this is an example of mutation code coverage. Looks very simple to regular code coverage, but the difference is that it shows which types of mutations it has introduced and which of them have been killed and which of them survived. So really nice report. So you can do on your whatever project that you have, and you will see that. Actually, this is the same algorithm, and you can see that I was saying, okay, we have introduced true here, and this is only a single mutation. But the actual tool even found another one, which said, okay, we change a boundary. Boundary means that changing this operator to less equals. So the tool even said something that I was not even thinking about when I was preparing this presentation, and it was like, oh, nice. So test selection. So as I told, line coverage, also test execution speed and test naming convention. Those two are not so important. They are mainly used for ordering results. Running Pit, you can do it on command line, use Maven, and if anyone still uses Ant, Gradle. So mostly all the tools that are in Java ecosystem. If you use any other tool which is not JVM based, I think you will have also many options like running on command line and running with your build tools. Okay, Maven usage. So you just generate a report, or you can use it with version control plugin. As I told, like you only look into changes that are relevant to what you're working now. So this is an example. And configuration, like we can introduce mutations in our dependencies quite far away, and you can configure how far away to look. For example, if you have a class and you have a test which tests this class and then introduce mutation in that class, this is like zero length dependency. If you introduce mutation in some class that this class is using, this is already one step away. So you can control this distance with this configuration parameter. And also you can limit number of mutations per class, because in theory you can generate infinite number of mutations in your code. Also you can activate, deactivate mutators. For example, if you have a legacy project, maybe there are a lot of patterns that are like you don't want to deal right now. And you can extend the tool. So what about TDD? So what I found out that it influences my code a lot. And it doesn't mean that it influences in the best way, but most of the time it's very good, because you start to understand, like, for example, that equivalent mutation with not equals and less than, it changes. Like you start to think like, okay, maybe I should use more less than and so on operators instead of using that one. So this is how it can influence it. Also, it helps to spot dead features. For example, you're removing something from the system. You don't need maybe the law has changed and you're removing some parts. It's very easy to leave some dead code, and the mutation testing coverage will show you that you have some dead code in your system. And it also puts emphasis on minimal code to pass the test, as I showed in baby steps example. So my personal experience. So Pit is very useful when you just start learning test-driven development. It helped me a lot, like understand design and a lot of important bits. But it proved to be less useful when my code became very generic. For example, I put algorithm details into configuration, or decisions were based on database data. In that case, it was unable to introduce mutations because my code was so generic. And it's very useful on large projects and teaches to write isolated unit tests, because speed is very important and it forces you to write isolated tests to get a quicker feedback. So to summarize, code coverage highlights code that is not tested. And when you have code coverage, you can see what you haven't touched. So which part of the code was not executed. Mutation testing is highlighting actually what you are testing, and it shows which parts of the code you have asserted. So with this, I want to thank you.